Okay, so we're going to go into the Banach-Tarski paradox and the proof behind it. So to understand the Banach-Tarski paradox, we will get a little background knowledge on it. It was introduced in 1924 by Stefan Banach and Alfred Tarski. Paradox states that given any two subsets A and B of 3 space, which are bounded and have non-empty interior, it is possible to cut A into a finite number of pieces, which can be moved by rigid motions, translations, and rotations to form exactly B. Rearranging, so therefore, like rearranging a single ball into 2 balls that are the same size as the original ball, makes this paradoxical because the task just seems impossible when you're thinking about it just sitting around, right? So it seems impossible, but mathematically it is very possible, and we'll jump into that right now with an equidecomposable object. Okay, we can say that 2 sets A and B are equidecomposable and write them as such if they are disjoint sets, A1, so on, and B1, so on, such that the union with AI and the union with BI, where AI and BI are congruent to one another. So the creation of the disjoint objects are also congruent. And that is usually shown by taking a square and this triangle, right? So we're trying to get from this square to this triangle, right? But we bisect the diagonal of this square, and it gives us 2 triangles. Now, alone, these 2 triangles are already equidecomposable, but we can rearrange them to form this. So we're getting from A to B to C to D, essentially. So then we can skip all the steps in between and go A here to D, okay? So we can also do it in reverse. Say we want to go from this triangle to this square. We cut it up, rearrange it, and we get the square we started with. It's basically a little crash course in equidecomposable objects. And then from there, we will get into the free group decomposition. So a free group such that any 2 words on a specified set of generators are different unless their equality follows the group axioms. Okay, so this set's going to be defined as F2. So it's a set of all words. I use that very lightly because we were only using 4 letters to create these words. Okay, so using the set of letters x, y, x to the negative 1, y, we can create a list of words, but we can't forget to include the empty set, and we also have to note that x and x to the negative 1 will cancel, and y to the negative 1 will cancel each other out. Just like typical math, when you're dealing with exponents, they're going to cancel each other out, so they won't really be the same thing, okay? With that, we can say we represent in x with the set of anything beginning with x to the negative 1, it represents all the words that don't begin with x, right? And the same can be said for the y set, okay? So that's us partitioning the larger set that we began with here into these little subsets. So it's just different ways to write F2 in different set notation, and that will give us the ability to have different partitions. We want to have 5 partitions that we can use 4 of them and reassemble to create 2 copies of the entire set of F2, right? I can say that, but it's a lot easier to show it, right? Okay. So this is a beautiful little math shape or object, often called, well, not often, more often, I guess not more often, it is always called a fractal, right? Look, it's a fractal if you're aware of the shape. This is what it is. So if we're starting at the origin point here, x will go this way, x to the negative 1 will go left, y will go up, y to the negative 1 will go down. You see, we can't see anything that starts with an x and anything that starts with an x to the negative 1 are different. Also, anything that starts with a y to the negative 1 are different. Anything that starts with anything is pretty much different than the other, right? So we go to the right one, up 1, that is not the same word or same orientation of going up one to the right one, right? See, we end up in two different spots here, and that's how we kind of think of the fractal. Now, the important part of the fractal is it goes on forever and ever. This is just a minute sample of what it could be. So it is infinite in the sense that we could just continue this fractal on and on forever and ever until it just looks like a little blob, because you can't look at the parts separately for one another. So we go right, up, right, left, up, down, all over the place, however many times we want, and this is in 2 space, okay? So we've created our 5 partition sets, and we can reassemble 4 of them, right? So we have all of these, right? The empty set is contained within these, okay? S is this weird little shape, right? We made it a weird shape so we can make sure to cover all of the points along this axis while thinking when we expand these fractals, right? So when we rearrange R and T together, we create an identical copy of this original fractal, and the same can be said for S and U, right? We've created U. U is all the extra points. S is going to be all the points that start to the left or any point on this x-axis that we've defined. R is any point that starts by going up and Y, okay? And the green piece is any part that starts by going down, okay? As stated before, the fractal is infinite, so everything is really infinite within it. So we can expand to this size, right? So this little piece right here can become this big piece here because it goes on and on forever and ever. And then we can just slide it right down onto T, and it creates 2 identical copies of one original copy. That's the idea in 2 space that we kind of want to translate into 3 space with our free group of rotations, okay? So it is important to note that our free group of rotations, theta has to equal an irrational multiple of pi, and I have chosen the irrational multiple of pi to be cosine to the -1 of 1/3 or arc cosine of 1/3 as the irrational multiple, okay? We can find the group of rotations about the origin, 0, 0, 0, in 3 space in the same manner as before by choosing our irrational multiple, okay? So x to the -1, y to the -1. These are a little different. X and x to the -1 are if we have a ball and we're holding it. Those are the right and left turns, okay? And y is our forward and backward turns, so it's rotating along the z-axis versus the y-axis because the y-axis is contained within the ball, okay? So, moving on. We'll let G be all the moves you can repeatedly make by completing any sequence of x to the -1, y to the -1, okay? So there's where a lemma comes into place. If rho is 3 space mapped onto 3 space is an expression in G with the length n in reduced form, then rho 0, 1, 0 is of the following form, which the following form is right here where A, B, and C are all integers. So the following lemma rule, we can complete the math such that A and C are 0 and B is our 1/3 to the n with n as an integer greater than 0. Okay, so with a little bit of math that we've completed to prove that, the theorem for that involves the free groups of rotation is G is the free group. In other words, there's no non-trivial identity to G. Okay, so trivial identity is a 0 as an identity, okay, right? So there exists no non-zero solutions that act as an identity of G, okay? So that makes these trivial versus non-trivial, because non-trivial is 0 right? So the details of proving this are very lengthy, just because the proof can be shown by listing all of the possible rotations we can apply, with rotations forward and backward and left and right in Model 3, and that's not really possible to show since we stated before it is infinite, right? So it's hard to show, so I've omitted the details. If you're curious about it, you go look it up in my sources. One of my sources does dive a little bit into it, but I didn't think it was necessary to explain an already proven theorem in depth like I should have. Okay, so for the decomposition of the sphere, we can also continue on with a little definition that L is equal to basically 3 space, where x squared plus y squared plus z squared is less than 1, which gives us the unit ball, right? So now we're working with a unit sphere, okay? Now we want to partition or break up the ball missing its center, denoted by L prime. So it's L without that center piece of 0, 0, 0 into groups or orbits of G, right? So by definition, 2 points A and B belong in the same orbit if and only if there exists some rho in G such that rho of A equals B. Okay, so this is where we can get into the axiom of choice, right? It's pretty cool. You can the axiom is really defined as letting C be a collection of non-empty sets, and we can choose a member from each set that's in the collection. So there exists a function of f defined on C with a property so that for each set S in the collection. So f of S is a member of the whole set, okay? We use the axiom to pick our L prime out from each orbit, calling the set of all these points M. Therefore, we have the ability to end up with any point in L by applying the proper rotation from G to the correct element of M, right? So each of these rotations must be unique, right? We can go left and up, right? But there's no 2 rotations that'll get you to that point again. So you can't go up and left to get to the exact same point. It'll end up somewhere else, like we did show before with our fractal, right? So left and up won't give me the same thing as up and left. That's where we end up in different places. But there is something that you can do, or not something, there is a combination that'll work, but it's greater than 2, so we kind of negate it from our findings, okay? So all the points that lie on the axis, right, we'll call that set D. They're the fixed points of rotation. So since G is countable, and each point has one axis of rotation, as shown before, with X representing the X and Y representing our Z axis, right? The points that lie on D are uncountably many lines, okay? So this is where we kind of have to handle our leftover pieces, or the empty set, right? From before, we kind of just tossed it out and just figured it out with the fractal, where we had the non-empty sets and we just left the empty set out to rearrange the fractals, okay? We have to define a new set, J, and it is defined in this notation, right? Notation that means J is a set of all elements of M after rotations entirely consisting of x to the negative 1 repeated any number of times, right? So we just keep turning this thing, turning this thing, turning this thing, and it's basically giving us all the points on one of the hemispheres if we just keep rotating, 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 right? So we can rotate any of the 2 pieces to get duplicate pieces, much like we did in the free group decomposition before in 2 space, okay? And that is why we have these specific partitions, because they are encompassing all the points possible that could possibly overlap, okay? Now, right, we haven't handled the center because we've left the center out in that case to show the equidecomposability of spheres without their center. So with our center points, we have to show that L prime without D and L are equidecomposable, okay? So since the points of D lie on countably many axes, we can find a line through the origin that does not intersect D. Also, since the points of D lie on countably many axes, we can find the angle theta, like we stated above, theta, an irrational multiple of pi that we chose, such that by rotating by theta around the line, it never maps the point onto D to another point on D. For example, let rho be the rotation by theta, then rho n of D and the intersection of rho n with D are the empty set for all integers n and m, right? So it's defined as set E, kind of following the union of all powers of rho, okay? So how we're handling the center of the ball is we're going to handle it by using a circle, missing a single point, right? A whole circle is equidecomposable with the same circle missing a single point. This is often shown through a countably infinite hotel, right? We're ending up with a circle right here, right? All the points are full, so all of the rooms are full. But if old John comes to the hotel and wants a room, well, I can make a room for him, because since we chose an irrational multiple of pi as our rotating these customers throughout the hotel, they'll never end up in the same room, and there will never be a room on this circle that overlaps another. So we could simply tell everyone, hey, we got to rotate you all one room to the one room counterclockwise in our circular hotel, and that opens up a room right here for John, right? That's basically the idea of equidecomposability with a circle and a circle missing a point. So we'll use that knowledge for a ball without a center, right? We can make this circle going through the center of the ball, and the missing point of that circle can be in the center, right? So we conclude that the ball can be equidecomposable due to the use of our previous lemma, right? Due to this lemma, we can make the ball equidecomposable by making a circle pass through its center, okay? So all that gobbledygook does really come together here in the end, since we did show, right? The Banach-Tarski proof, the unit ball is equidecomposable with two copies of itself. We've shown through the decomposition that the sphere without a center, right, is equidecomposable with itself, okay? And we had the theorem in the lemma that associated the fixed points of the center to show equidecomposable between a sphere without a center and two copies of itself without a center. And the final theorem that we used, utilizing the lemma with a circle missing a point, shows equidecomposability of a solid sphere and itself, right? So what is my conclusion in all of this? This is a paradox. This paradox works because of many different levels of infinity and infinitely countable points with infinite density. To fully understand the working of the paradox, you have to understand all the infinities, how they behave, and help prove the paradox. It's really hard to prove it physically, since it is quite paradoxical, but mathematically, I mean, all the things are there to make this theorem make sense, right? We understand the levels of infinity. We understand that infinity is this great thing with many points. Negative infinity to infinity. We can create some random number, or there is a random number that exists that we haven't named yet, that we can find a spot for all along the line from negative infinity to infinity. That's kind of the case with the Banach-Tarski paradox. We're creating these finite number of pieces of one sphere, and then when we rearrange all these pieces, we can sort of find our way to create two identical spheres that are the exact same size as the sphere we started with. I just think it's pretty cool little thing in math that everyone should kind of dig into. I mean, I've only scratched the surface. I had 6 sources. There were 6 really good sources, but I mean, the theorem is quite old, I guess, from my perspective, since I'm 22 years old. It's old to me, but I mean, it's relatively new in the math world. So there's lots of stuff that we could still discover about it, and maybe we could even prove this physically, or someone already has, and I just haven't found it yet. But it's very interesting, and I recommend you going on and digging into it a little deeper if it does pique your interest. Thank you for listening.